this tutorial, I will cover the basics of the Mips architecture and how to write assembly code. I will assume you have basic knowledge of how to write code, how to read decimal, binary, and hexadecimal numbers. Some of the topics I will cover are the structure and syntax of Mips, big endian and little endian byte order, system calls, basic instructions, extended instructions, and the difference between the two. The Mips instruction set architecture, or ISA, is basically a model of a processor, and Mars is the simulator that implements Mips and allows us to use it. You can download Mars by Googling Mars Mips Simulator. I will clarify later in the video, but for now, registers can be defined as slots that hold data the programmer can access, whether that means putting data in there or taking data out and using it to compute a new value. The programmer is the one controlling how the data is being used. An instruction consists of the name of the instruction, followed by the parameters it needs. Parameters are pieces of data the assembler needs in order to do that instruction. For example, the add instruction needs one register to save the result to, and two additional registers or values that will be used to compute that result, making 3 total parameters. Each instruction varies in the amount and the type of parameter it needs. From now on, when I describe the number of bytes a certain piece of information is, or how many bytes a register stores, just any information about the size of data in the program, know that I'm specifically talking about the Mips instruction set. A bit is the smallest unit of data a computer can process, and it could be equal to 0 or 1. Different computers and computer manufacturers have different implementations regarding what to call groupings of bits. If we look at a completely random hypothetical system, 8 bits could equal 1 byte, or 4 bits could equal 1 byte. It completely depends on the way the system was designed. The Mips instruction set run on Mars is 32 bits. This means each address is 32 bits long, each instruction is also 32 bits long, and each register can hold 32 bits. 8 bits is considered 1 byte, 2 bytes is considered 1/2 word, and 4 bytes is considered 1 word. Another concept to understand in Mips is byte order. There are 2 types of byte orders, big endian and little endian. Remember, when looking at a number, the most significant byte is the one with the biggest power, and the least significant byte is the one with the lowest power. Big endian means that the most significant byte, or the big end, of the data is placed at the lowest address in memory, and the rest of the data follows. For example, let's say we had a block of memory, and we want to store the word 0x abcd0123. In this word, AB is the most significant byte. Therefore, in big endian byte order, it will be stored in the lowest memory address, so 0000, and the rest of the bytes will be stored in the next available addresses. Little endian is when the least significant byte, or the little end, of the data is placed in the lowest address, so basically big endian but in reverse. If we look at the same example, but store it using little endian, the byte 32 will be stored in the lowest memory address, 0000, and the rest of the bytes will be stored in the next available addresses. Byte order is another example of how different systems use different methods of organizing their data. For example, the Intel x86 microprocessor uses little endian byte order, and Macintosh uses big endian. In Mips, we use big endian. So when you make a string in Mips, let's say the string ABC with a null terminating character, then null terminating character is represented using \0 and holds the value of 0. One of its uses is letting the program know when we reach the end of a string. This string is stored in 1 word, since it's 4 bytes of data, including the null terminating character. And it's stored in our data section in big endian byte order. So if we go to the execute tab and we look at our data section, we can see that A is stored in 10010000. B is stored in 10010001, and then so on. Using this knowledge of how data is stored, we can understand why a block of data can be referred to by the address of its first byte. When you use the load word instruction, the only byte that is looked at is the big end of the block, or the most significant byte of data. In the strings test string and small string, test string holds the address that A is stored in, and small string holds the address that 1 is stored in. Printing the null terminated small string 123 requires the same amount of data to be loaded into the A0 register as printing the null terminated test string, even though small string has 4 bytes of data and test string has 27 bytes of data. A hashtag or pound symbol means the rest of the code on that line can be ignored and treated as a comment. Notice that comments will show up in the execute tab with your code if you place them on the same line. I found this extremely useful when debugging code, just being able to read in plain English what that line of code does. Okay. So in our code, we need a .text and a .data section. The .data section is an area in your code that's dedicated for declaration of values. The most common use for this section, from personal experience, is for defining strings, which there are 2 ways of doing. we can use the .ascii directive or the .asciiz directive. The z determines whether we have a null terminating character or not at the end of the string. Note that when a string doesn't have a null terminating character and you're printing that string, the code might print strings that come after that string because the code only knows to end that string once it sees a null terminating character. The .text section is the area you write all your code or instructions. In the .text section, we need a label called main. Main lets the assembler know where to start executing the code from. At the very end of the .text section, there should be a exit system call. I like to think of system calls as a way to make the system do something like print a number, print a string, exit the program, etc. These are just examples of what you could do with system calls. To make the program execute a syscall, you need to load the number of the syscall into v0. Next, you need to pass any arguments that particular syscall may need. Every syscall requires this information and can be found in the help tab. The last step is to do a syscall. Every time the assembler sees a line that has syscall in it, it will take the current value of v0, telling it which syscall to use, and if that particular syscall needs arguments or inputs, it will take whatever values in a0 through a3, depending on the syscall, and will use those values as arguments. A potential error may come from not using the correct instruction when loading arguments into the A registers. If the syscall is expecting an int, let's say, and you pass in floating points, then that could cause problems. You might be asking, oh, why are you using load address to load the string into A0? Well, if you remember, strings can be referenced to by the location of its first most significant bit, and that location is just an address, and we store it in test. If we go to our execute tab, we can see that test has this address, which is equal to A. Inside our .text section, we can access information or store information to registers using the load and store instructions. Mars is great because it tells you the syntax for each of these instructions and how they should be set up. For example, if you just start typing LW or LB, it will show the different alternatives of that instruction that you may need. You could also go into the help tab and look under basic instructions or extended instructions. The extended instructions are instructions that could be implemented using the basic instructions, but make the code look neater or easier to understand. The extended instructions are converted to basic instructions during assembly